I welcome you all to CIT Quantum Hackathon 2022 workshop series sponsored by IBM Quantum as a part of Biscuit Fall Fest. I thank all participants for showing interest in learning. Finally, the day has arrived to learn new things and gain knowledge. It's my privilege to welcome our Honorable Chief Guest and Speaker, Ms. Kavitha, Assistant Professor, National Institute of Engineering, Mysore, Karnataka. He is also serving as an IBM Quiz-Kit advocate and has 10 plus years of experience in teaching and research. She published over 12 plus articles in Sci and Scopus and other indexed journals and conferences. She published 2 papers in reputed journals along with 12 international and national conferences. Her research interest includes quantum computing, quantum machine learning, data science, and VLSI. Ma'am, once again, I welcome and extend my sincere gratitude to you for taking your time to share your knowledge on quantum experience on the topic of quantum machine learning demystification. The session is all yours now, ma'am.
Yes, I hope you people have little knowledge about the machine learning. So, can I get an answer before I start the session?
Yes, ma'am, we know the basics.
Yeah, that's good. So here I'll be talking about the quantum machine learning topic. So I don't make you things difficult. I'll tell you how the machine learning concepts are taken to quantum and what made this machine learning things to be worked on the quantum. So how it is efficient to make the machine learning, any methods to be learned on a quantum is easily taught in this talk. So any question, any queries, you can stop me in between and you can put me your queries. So here in this talk, I'm going to give a brief intro about the quantum computing. So here I'll be rushing speed with the basic topics as you have listened to many series of talks regarding what is quantum computing and why you require quantum computing and what are the current trends you have in the quantum technology. So I'll be pitching mainly into my quantum machine learning concepts and how it is different from the classical and how it is done in the quantum, and a small demo session of how to run one of the machine learning algorithms. Since we know that support vector machine stands as SVM, it's a very difficult machine learning process, and how if we want to have a huge data set to be made classified into 2 classes, how difficult it is to do in a classical machine and how efficiently it is carried out in a quantum machine will be taught in this session. So, coming to a brief intro about why we are studying this quantum computing. So, all of you know about the chips what we have in our motherboard, like the IC chips. So, the number of transistors which are used to build this ICs are increasing. It is getting double for every 18 months. So think of a scenario if the number of transistors goes on increasing like this, there will be a trend where this devices will be impacted on the, or it will be embedded into a chip in such a way that there, if any a small increase in a voltage causes a large amount of the current to be flowing inside the chip. You can see here the voltage which is applied here makes the current to be leaked into a substrate section. So you might have seen how the MOSFET is designed. We have a substrate layer, we have a source, drain, and the gate layer. So the current which is voltage which is provided into a source causes the current to flow from drain to the source. So if the devices are very small, a small voltage, if it is increased to a little bit small range, it allows a current to flow from one region to the another region. So little increase in voltage causes the current to be leaked into a substrate. So this is a very serious effect, and we call this as a second order effects in the VLSI design. So we have to think of a scenario. So if the device is shrink, or if the device is made more and more smaller, that is, if it is designed in a nanoscale, we have all this series of effects. So in order to overcome these effects, now we have to think of some other architecture. So that architecture which works at an atomic scale. Now we are is thinking of a nanoscale, that is which is working in a nano size. So now we have to think of some different architecture. So that architecture is nothing but our quantum architecture. So you can see here how the number of transistor which was there in an earlier year and what is the number in the year 2015. So with this very increased number of transistor, it is very difficult to build a chip. So next we have to think of what we have to do with the different architecture. So before we see why we have to study this quantum technology, so we can see the hype of it. We have the different types of technology. We have the current trends. We have machine learning, artificial intelligence, IoTs, and various different technologies which is coming up as trendy technologies. So if we see where this quantum technology is standing in the today's scenario, so in this greater hyperscale, which is decided every year, this shows the technological growth of each and every technology introduced. So we can see here the quantum ML, that is the quantum machine learning, which is given in orange color. It exists for more than 10 years. So that is given by the greater scale, which was decided in the 2021 year. So based on this, we can now think what is the speed up we are having with this technology. And coming to the roadmap, when it started and where we are now. So it started in 1935 by the idea of the Einstein. And now these ideas were taken up by the Feynman, Richard, various different scientists. And now we are with the quantum demonstrating the effect of quantum demonstrations. So IBM is the one great company which has given a hands-on experience to work on this various quantum technologies. So coming to what is quantum technology, so we know that as we have discussed, as you have listened to various talks, the quantum technology is the technology where we are working at an atomic scale levels. So at that atomic scale levels, we can no more think of the classical rules, like what is the what is the bits and zeros and ones. We cannot that no longer stands. So at this point at the atomic scale, we have to bring a new type of method that is called as a laws of quantum mechanics, which takes properties of entanglement, superposition, and various other properties like coherence, interference, superposition, entanglement, various types. So if we take a difference between the classical and the qubits, in the classical bits we just had zeros and ones. But since in the quantum we are working at a subatomic level, along with the zeros and ones, we have the superposition of the zeros and ones, which makes the computation to be executed parallelly, and in this parallel execution we can expect the speed to be in range of terahertz. So based on this various different beautiful properties of this quantum, we can find this quantum and various fields of applications like cryptography. And quantum cryptography is the one field which is in a very trendy options to many researchers. And we have the quantum medicines where the different drug discoveries are done in this field, and materials and machine learning, searching of a big data analysis. Any big data analysis can be easily solved using this quantum technologies. So, as is about quantum works with the quantum mechanic laws. So, coming to this quantum mechanics laws are nothing but the superposition, entanglement, interference, and quantum tunneling. So, if I just tell in the words, it is difficult to understand what the superposition or the entanglement state. So, this pictorial representation gives the idea to think of how actually the superposition looks like. So instead of having just zeros and one bits as we have in a classical, here in the quantum we have the superpositions of zeros and ones. So you can see here we have the states of zeros and ones popping up simultaneously. And this is the property which we have with the quantum. So using this property, we do the computation. So along with this, to make the computations parallel, we have this one more beautiful property which is called as entanglement. So in order to make any classical methods to be working in a quantum, we have to entangle the states. Only the states, if we are entangled, then we can achieve this quantum property with that method. So entanglement is nothing but if we know the state of one of the atom, we can directly tell what is the nature or what is the behavior of the another atom. So they are like connected to each other, irrespective of distance, whatever the distance they are placed with. If we know the one property of one atom, we can directly say the property of the another atom. So that is called as entanglement. So in this entanglement, how we achieve parallelism is nothing but we just do the computation for one of the bit. So other bit is just doing the reverse of it. So that is how the process goes on. So interference is the one, again, the one of the beautiful properties. So when we see this interference as a property, we know that when we have the maximum peak in the waveform, in the classical, we do the computation. So you know that if I take an amplitude modulation, with a maximum amplitude, the informations are carried out and it is passed to the other end. But what if the waveform get bombarded with some of the particle which is present here? So this effect is called as, we call this as a quantum tunneling as well. So on bombarding of this particle, we see this, there is a loss observed here and we don't take this loss into any account which we do in a classical. But actually in a quantum, when heavy objects hit into any of the particle here, when the waveform hits into this heavy object, it leaves a vibration going to the other end. So this vibration is again taken for the computation. So even this loss is also not discarded. They are taking even this vibrations to do the computation. So the quantum tunneling is also a very important property here in this to do the quantum computations. We should have all these properties embodied. So with this properties, we use various quantum gates to build the quantum circuits, and these quantum circuits are again directly used to build a machine learning model. So again, not speaking much about this quantum gates, since the people present here know what this quantum gates, various quantum gates are. And since we are working on the machine learning concepts, and in this machine learning concepts, we want to design a quantum circuits which throws the output as a matrix or the vector products, and these vector products are taken for the classification algorithm to do the classification process. So we use these different quantum gates to build the quantum circuits, and always remember, when we are using this quantum gates, don't only use the unitary gates. Along with this, use some control gates in order to put the state into a quantum entanglement state, so that at the entanglement state we can achieve the maximum quantum properties. So entanglement, how to do the entanglement properties? One of the method to use the entanglement is, first we place the Hadamard gate, and then we place a C0 gate to make the qubits enter into an entanglement phase. So I told you what the advantage we have with the entanglement in the previous slide. So moving with my main talk is on quantum machine learning. So I'll just concentrate on this topic. So machine learning, we know that we are making the system to learn. We are making any of the model which is designed to learn by itself is called as a machine learning. So also we know that what is quantum computing. So quantum computing is a different computation technique which is used to perform the computation at the fastest speed. So if we mix this quantum and the machine learning together, we call it as quantum machine learning. So here we are making the quantum computers to learn by itself. That is by using the quantum information processor, and give the input to the quantum information processor, and this data which is fed into a quantum systems make the system to be modeled in such a way that it will learn by itself. So that is the process of quantum machine learning. So you can again stop me here and ask me a question. So, if the classical machine itself is making a classification, or if it is doing a machine learning method training itself is done very efficiently by the classical machine itself, why do we need this quantum to do the quantum machine learning process? So to understand this quantum machine learning, first we have to know the limitations of classical machine learning. So some of the limitations what we have in the classical machine learning is, whenever we do a big data analysis, when the data set which is fed into a system is very huge, you can think of a computation which is done by a classical machine. It takes lot of time to do the computation and give the output. So the time complexity of this machine, classical machine, increases. So in order to make the computation process speeder, what we do is we feed this data into a quantum processor and we make the computation happening in a parallelly, and then we read the data and then we do the classification process. So this parallel computation, which is done in a quantum processor, makes the process speeder. So that is one of the main advantage we have with the quantum machines. And there are various machine learning algorithms. Like in the machine learning, we have the supervised and the unsupervised type of methods. Since supervised is the one where the machine learn based on the labels provided, and in unsupervised we don't have the labels. Even without having the labels, the machine is trained to learn by itself. So based on the supervised and unsupervised, again this quantum computers circuits are designed or to take the data and to do the computation and then throw the output. So how it is done? So for that, we have this process showing how the classical machine learning is performing its task and how the quantum machine learning is performing its task. So in the classical machine learning process, we take this any of the machine learning model and we feed the data into the CPU, that is the processor. So in the CPU, how the data are read? So in the CPU, the data are read one after the other, that is in a sequential manner. So the time taken to run this process is very large. So in the uh, inverse effect, if I think of a different technology that is in a quantum, if I feed the same data, see the processing, the thing how the quantum is doing. So quantum is taking the data and it is doing the computation parallelly. So we have this parallel computation which is done in a quantum processing. And after the parallel computation, the data is then analyzed. So we have a many number of superposition states here to do the computation and the results are thrown. So if we say the time taken in a classical and the quantum, we can see the advantage what we have with the quantum. And with respect to the processing, if this is happening, if quantum is giving a high processing speed, how it is established. So suppose if I take a 3 bits, if I feed this 3 bits into a quantum computer, so this 3 bits is taken as 8 different states. If I put this 3 bits as an binary inputs, it will stands from 000 to 111. So this 8 different states are fed parallelly to the quantum processor. In case in a classical machine, if it is 3 bits, each trial will go one by one. Whereas here in the quantum, all the 8 states are put together into a quantum processor. And all these 8 states do the computation and throws the output in the 8 states itself. But the expected output is only 1. So expected output should only be 1. So what we do is, after getting the output, we put the measurement. So whenever we do the observation on the quantum processing, the observation collapses to a classical type. So even though the computation is done parallelly, on observing, it collapses to a classical type. So it is like flipping a coin. So when I keep the coin on the hand, I know whether it is a head or tail. When I flip it on the air, in the air it will be zeros and ones. That is called as a superposition state. I don't know what way it is head or tail. So at this superposition state, we are doing all this computation. Again, when it falls down, it collapses to either head or tail. So that is the state what we have here. So after doing the computation, give the output and read the output. So that is the processing, how it is done in a quantum machine. So classical, bit by bit, quantum, parallel. So based on this, the various types of application, as I mentioned earlier, we have this applications in quantum machine learning applications. We have in a wide range of application in a face recognition, genetics, recommendation system, finance investment, self-driving automation, entertainment services, and etc. So pitching into a main topic of support vector machine in a machine learning concept. So this is one of the very important algorithm to do the classification. In a support vector machine, how to do the classification is, if I'm thinking of just a binary classes. So if I take a data, and in that data, if I have only two classes, either 0 or 1, to do that classification, it is very easy. So either I can go with the linear regression, logistic regression, any of this classification method to do the binary classification. But why actually support vector machine? This is because when I have a huge amount of data, then the separating of that or classifying that of data using a linear regression or the logistic regression is difficult, because we can't simply draw the line in between the two classes. So we have to expand it to give the proper classification. So that is done by support vector machine. So support vector machine is the one method which is used to classify the huge data. Whenever the data set is very large, go with support vector machine. And whenever the data set looks complex, then again go with support vector machine. So for the binary type of classification, how does the support vector machine learning work? So support vector machine, so those who have explored the machine learning concept, so support vector machine is simply draws an hyperplane and classifies the two data. So this hyperplane has a margin. So this, based on this margin, the classes are divided into two sets. So the hyperplane with the value, this is a straight line equation, that is ax plus b, which you have studied for a straight line equation. We have given this as wx plus b. All the data which is greater than 1, throw it to one class. All the data less than 1, throw it to another class. And we draw this hyperplane and we segregate this data. So in the support vector machine, and we have to decide the margin of this hyperplane very thoroughly. So if this hyperplane is very large or if it is very small, both has some drawbacks. So if it is very large, then there are chances of this data getting residing inside this hyperplane, and this data which resides inside this hyperplane are considered as errors. And more the error, it says that the machine is not trained properly. And even again, if the hyperplane is too small, if it is too small, again, this data gets mixed with the other class get mixed with the other class, and again, there is no proper classification done. So selection of this hyperplane is very important when we are doing an SVM type of classification. So to do that, we have to think of an optimization process. So optimization process is based on the width of how much we are selecting for the hyperplane. So this is width square divided by 2. And solving this equation of classification, we can write this SVM classification equation as yi wx plus b minus 1 greater than or equals to 0 for all the values of I ranging from 1 to the maximum number of data we have. So again, in order to optimize, we can apply the regularization, where we find out how many data are present inside this hyperplane, and we take that as an error, and we put an optimizers to remove those errors and to put an optimizer to minimize those datas and throw those datas into proper classes. So that is how actually the SVM works, and how this SVM is taken into classification. So this is just I have shown for an binary set of data and how this binary set of data is placed. So if this data is placed like this, drawing a hyperplane is very easy. So just draw the line and two parallel lines to it. So this constitutes an hyperplane and it is very easy to do the classification. So think of another scenario where we have the data present like this. So drawing an hyperplane to this is impossible. So in such a case, now we have to think of some other method, shifting of this 2D data into a 3D space. And that is called as a kernel method. So throwing the data from the 2D to 3D is called as a kernel method. So how actually this is done? So if I have the data is present in the segregated manner like this, so we throw this data into a 3D space. So in the 3D space, some of the classes are present above, some of the data are present below. Now we draw the hyperplane like this. So that hyperplane gives the classification of one of the classes above and one of the classes placed below. So this is how you can see in the animation. So drawing the hyperplane on the 3D space and classify the two datas. Yes, even taking this into a 3D space and doing the classification in the 3D space, it is actually done in the classical machines also. See the set of data. Again, the set of data what we have is having only two classes. That is, when I say classes, it is mentioned in the different colors. So one class with the red and another class with the green. So if I have two classes, yes, I can convert it into a 3D space. It is called as, I can select a polykernel SVM and I can draw the hyperplane and I can separate the two classes. So think of a data which has more number of classes. So if I have three or five classes. So in such scenario, so what can I do or how to do the classification if the number of classes are huge? So can I do it in a classical machine? Or can I put just this classes into a 3D space and draw an hyperplane to classify all the five different classes? So as the data set becomes complex, drawing an hyperplane using a classical method becomes difficult. And also, so since we are drawing an hyperplane, after drawing an hyperplane, we have to do the computation to segregate the data into two classes. So if the number of classes are more, I have to draw multiple number of hyperplanes and I have to do the computation. So this increases the computation complexity. Now comes the question, how to decrease this computation complexity. So as the data is a huge number of, and it is having a huge number of classes, the computation has increased in the classical machine. So now we have an answer for this. We have the quantum machine which decreases the computation complexity by performing the operation parallelly. So that is what done in a quantum machine learning methods. So in the particularly with the quantum SVM process, what process we do is first, as usually as we do in a classical machine, we first clean the data set. We do an PCA normalization, min-max, and we clean the data set and we keep the data set to a reduced format. And after that, we apply this quantum circuit. So which takes the data from lower dimension to the higher dimension. We call this dimensions as a Hilbert space, and all the computation takes place in a Hilbert space in a quantum process. And how this encoding is done? By drawing some quantum circuits. So how these quantum circuits are drawn? By using the quantum gates. So the quantum gates which has to be used is, we can use an unitary gates, you can use the control gate, rotational gates, phase gates, swap gates, etc. But in order to achieve the quantum property, we should have an entanglement. So how to get the entanglement? taken Hadamard gate and used some quantum controlled gates and see how this entanglement is reached. So how to do that? Take a classical data and feed it into a quantum circuit, and this quantum circuit should have an Hadamard gate and some unitary gates. So it is not mandatory that all the process should have an entanglement. Even without an entanglement, also we can achieve the classification by using a quantum circuit. But if the quantum entanglement is introduced into the circuit, then we can have a more quantum property introduced into our process, and we can see and very good results with the quantum machines. So here for doing I have not shown the circuit here, I have just formalized this encoding. So this encoding shows that I have an Hadamard gate, some unitary gates, which has two times of repetitions, and this encoding circuit is drawn. So even this encoding, what is this unitary gates? Unitary gates can consist of any phase gates, swap gates, and control gates. So unitary gates, I have formulated this as it has some, you can see here, the Z gate, the Pauli Z gate, which is imposed by this Hadamard gate to do the computation. And some of this, to understand what is this encoding is, taken an input data, it has to be converted into a quantum state. So how it is done? To explain that, so we know that when I take, I hope all of you have used an IBM composer. So in an IBM composer, initial state for the any of the gates, it starts with a 0 bit, 0 qubit. To convert the 0 into the 1 state, we will be posing a NOT gate. That is an X gate in the quantum gates. And this to do the encoding, all this 0 initial state is given to this quantum circuit, and the output is, and this quantum circuit performs a parallel computation and throws the output. So based on this encoding method, we have different types of encoding methods. So I'll give an example of one or two encoding methods. So this is one of the encoding method. So suppose if my data, see I have taken a very small data, when I take any of the data set itself will be of very huge. So this I'm showing for an example, if I have a data set which is of 1001 type. So how to put this into a quantum state? So one, I know that initial states are 0. To make it into 1, I have to impose an X gate here. So this gives 1001. And when I see the output of this is, I can see that it is simple like a classical machine. Simple like a classical NOT gate. So in this type of unitary type of encoding or unitary type of encoding method, we don't see any quantum advantage. It is similar to that of a classical one. And this type of encoding is called as a basis encoding. Now, in order to have an advantage of something to do with a quantum type, so I can have some unitary gates. As I said, these unitary gates can be a Pauli gate, swap, or a control gates. And here the unitary gates is mentioned with some data and some angle. So suppose if my data set is something like this, something in the floating points which has an imaginary numbers and sorry real and the imaginary with a plus or minus sign, then how it is coded? So that is coded by using a unitary gates. So this taking this data into the unitary gates, now you can see how my quantum computing is performing its task. So all this data are put into parallel computation. And all this data are performing parallelly and throwing its output in the probabilistic nature. And we have to do this computation multiple number of times. Since the output obtained is a probabilistic type, we have to run this circuit multiple number of times in order to get the proper output. So here I have not applied the measurement. So once you apply the measurement, all the outputs will collapses from the parallel to the series type. So here I will observe a single output which will be a classical type. And the same thing which is observed in a block sphere, you can see how all the data are put in for the parallel computation. So any doubts still here? anything you want to ask me? Any queries? Okay. Assuming that I can move forward. Uh, Next is, once we have this, how to do the encoding, take this encoding circuit and draw your own encoding circuit and take the input data and apply the measurement and see the output. So now this is what we have to do with the classification in quantum. So for example, in the quantum SVM, how we do the classification is, so encoding process, we call it as a feature map. Drawing a circuit using an encoding process, or we drawing a quantum circuit in an encoding process is called as a feature map. So we have to design that feature map. So this feature map converts a data of classical into a quantum, and this is like something like a parameterized circuit, where we have different types of parameters. We have angle parameters theta, we have a radian parameters, and it will be phi and xi parameters, which can be varied to do the various type of angle rotation and do the computation. So when we are drawing this encoding circuit, we should measure what is the circuit depth. So depth should not be very large, or because as the quantum circuits number of depths increases, the complexity of the quantum circuit also increases, and it requires a large area in a chip to be designed. And also mapping the function of that is from classical to the quantum has to be done in a proper format, and what are the gates we are using to do the computation should also be measured properly. And when we are doing this encoding process, we have different order of expansions, like second order expansion, ZZ feature map, Pauli feature maps, different types of expansions. So that has to be chosen properly. So once we are ready with this encoding circuit, this is the main thing what we have, what makes different from a classical to the quantum. So once we are ready with this encoding circuit, so the other process is same as that of the classical thing. So we may make a measurement, and to do the measurement, we take a backend. So since we are running all these quantum machines with the quantum processor, we have to select a quantum simulator properly. So for that, we will be selecting a backend, and how many number of times the circuit has to be run to get the proper output. So that we call it as shots, and the type of class. So when we take a data set, it can be of multiple class or it can have binary class. So we have to mention that in a quantum instance. So once running this quantum instance, all the parallel computation collapses into a classical output. So this classical output is again fed into a SVM, classical SVM process to do the classification. So only thing is we are doing the computation. That is, we are decreasing the complexity of the computation by using this quantum circuit, and all other classification process is similar to that of classical SVM. So allow us to give a demo on how does SVM work. I'll show you both with respect to a classical approach and also with a quantum approach. So please make me sure whether this coding is visible. So can you please see this coding?
Visible.
Thank you. Okay. So this is, I have taken a wine data set. As I said that when we do a classification for a two number of classes, it is very easy. But when you have a number of classes are large, then doing a classification using a classical machine is time consuming. And also the type of results which is thrown with a classical, it may be less sometimes. So how it is done in a classical machine, how it is done in a quantum method, it is demonstrated here. So in a classical machine, what we do is we first select the data. Since the data of one wine, it is present in a data set sklearn. I have imported from that from the sklearn. This wine is data set is taken, and the labels and the data are separated, and they are split into train part and the test part. And then we do the pre-processing steps. As I explained, for a pre-processing, we will be applying a PCA, and we will be applying a standard min-max scaler, and excuse me, to minimize the range of the data from a small to a smaller range. That is, the data to be residing in the range of +1 to -1. So that condenses the data. So after this pre-processing, I know that I have the number of features used in this data set was 13. Now I'll be selecting just 3 features to do this classification. So you can also see the number of classes what we have with this wine data set is A, B, and C. We have 3 classes and 13 features, and this data set has 178 datas. So among the 13 features, I'm selecting just 3 because you know that the number of qubits are limited in the quantum processor. If I have more number of features, then I have to select so many number of qubits. More the number of qubits, again, it makes the system complex. So for timing scenario, I'm just choosing the number of features to be 3. Again, the same thing which I have done, the splitting of train and test. So here, for the demonstration purpose, I have selected all the datas. That is all 178 datas. I have split it to train and test. Train part should be 70%, and the test I have selected 30% of the data. And on condensing of this data and doing PCA with applying PCA, this is how my data looks like. Wine data set. So now, coming to the classification with the classical SVM method, I have taken the library to do this classification, that is a SVM classifier. I have taken a kernel as RBF. I said in order to, when we have this more number of data, what we do to draw this hyperplane, we convert a 2D into a 3D, and we have to choose various types of kernels. So different types of kernels we have in the classical types are RBF, sigmoid, poly, various types. So RBF is a very widely used kernel in the classical type, and this gives a good result since it is taking an exponential manner of classification, and the computation done with this kernel is also bit speeder compared to the other type of kernels. So I have chosen this as RBF, and the regularization factor. So regularization I have shown you with the formalization. So more the number of regularization factor, I can minimize the errors. So regularization I have selected it as 0.5. Again, you can play around this algorithm by increasing or decreasing this regularization and checking the performance metrics. And with this, I have taken a fit of sample and train, and I have now running this algorithm. So we have this output obtained with the SVM classification of a wine data set. So you can see here with the decision boundary how the 3 different classes are classified. So there is a small error with some of the data getting merged with the other classes. So because of this data moving to the other classes, we get some results to be of less. So we can see that by taking the various metrics. So if I compute the accuracy, so after training, the test part has to be taken to check how the model is trained. So the test part, it is giving an accuracy of 96. And also you can see the training and the test part accuracy together. So the train, it was 96.82. And when I give the test part, yes, that is also classifying properly. That is also giving 96.15, which is which says that the model is trained properly. And if I see this time taken to execute this. Yeah, this is not given properly, so I'll show this again. So various performance metric you can draw once you get this model trained. So with respect to that, I have drawn the confusion matrix as well, which gives a true positive and true negative types. You can see how the class 0, class 1 and class 2 are separated. The class 1 is perfectly separated. The class 0 is some part of the class 0 is moved to class 1, and if I take class 2, yes, the class 2 is also 100%, it is perfectly classified. And again, yeah, this is the repetition thing. To draw the ROC curve. So ROC curves gives us how efficiently we have done the classification. So this ROC curve, all this library are available, how to draw this ROCs and all that is available in the net. So all this performance metrics, once you are ready with the algorithm, you can take any performance matrix and you can draw this diagrams. And more the curve towards the margin, it indicates our model is trained properly. It is more towards this margin or more towards this diagonal line. It indicates that our model is underfit. So this type of range with this lying in 97 and 92, it says that the model is well trained. So this is how we get different types of scores. Also, you can see the precision score, recall score, accuracy score, reference score. So all this performance metrics of the machine learning, any model we take, these are the performance metrics we have to learn with the machine learning types. So the same thing is shown here for an SVM on wine data set. So this is how we do actually in the classical way. So not digging much into a classical one. So moving into a quantum type, how it is done in a quantum type. So you want me to run this whole process, or is this enough? The demo is enough. If I just show the demo, is it sufficient, or you want me to run this each and every cell?
Demo would be sufficient.
Okay, fine then. So to run a machine learning model on an IBM quantum processor, so you can do this uh, machine learning model quantum SVM on the IBM quantum labs, or you can use a local host to do the same process. So I have used the local host to do the processing. So I have loaded the IBM account and I'm running this process in a local machine. Then load this IBM account. First step is, this is very important. So take all the Qiskit libraries and data processing, as I said, the pre-processing has to be done before we apply it into a quantum machines, because the number of qubits are limited currently in the quantum processor. So we minimize the number of data and then we pass it to the range. This is pre-processing. It is again similar to the classical type, like how we apply PCA, min-max, standardization, etc. And after pre-processing, we do the split of train and test data. So again, we have chosen here as 70% of the data and 30% to the test. And we have chosen the number of features to be 3. So this is again the same as the classical one, how we visualize this wine data set. And now comes the encoding process. So here, before I do the encoding process, I have set some of the libraries. I am using a ZZ feature map. I can use ZZ feature map or a poly feature map. Any of the feature maps you can use to do the encoding process, or you can draw your own feature map. We call it as a customized feature map, and you can do the classification. So the inbuilt feature maps we have are Z feature map, ZZ feature map, poly feature map, etc. And to put this, first I'll explain you what is this feature map. So feature map is nothing but the encoding process which I explained in the slides. And to draw this feature map, I have chosen a poly feature map. You can either choose ZZ feature map or a poly feature map. So in the ZZ feature map, I have only one option, that is I should go with the Z gates only, poly Z gates only. But when I choose this poly feature map, I have an option to play with different combination of polys. So that is, I can go with XY, XX, YZ, YY, ZY, or XYZ. Different combinations you can put, and you can train your model, and you can see how at what best poly combination I get the good accuracy. So that is the one research thing which we have. And yes, selecting this feature map for a data set, it is not a standalone process. We have a different feature map for a different type of data set. So how to select this feature map is still an open question, and still the research is going on how to give a standalone feature map. So till now, what we do is we give a trials, different number of trials, and at different number of trials, we find out which trial is giving a best result. So in that way, I can say you give the different combinations of polys and find out which best combination is giving the good result. And also when selecting this feature map, you can put this polish in n number of repetitions. You can put it as only one number of circuit, or you can put that as two or three number of same circuit repeated. So I have given the repetition as 3. So you will be having poly X, Y, Z, Y, Z, Y, Z. So 3 blocks of YZ will be repeated in this circuit. So you can even vary the repetition, and I can see how well the circuit is performing. So don't go for more number of repetition. Try to keep the repetition as minimum as possible, because we want to make our circuit look simple. And as the circuit becomes more, as the number of gates becomes more, it will be difficult to be placed on a chip, and as it will take a more area on a chip. So see that at what best repetition we get the best result, and stop there. And along with us, along with this, take all the training data and put it into a feature map. So once we are ready with the feature map, if you want to see how this feature map looks like, before I give this SVM, okay, it's already taken. So you can see here, since I have given Y and Z, my combination was Y and Z. You can see here in my circuit. So initially I should have an Hadamard gate. It is by default because I want to take the data into a superposition state. So superposition is given by this Hadamard gate. So after that, I can either go with an entanglement process, or I can go with an unitary, or I can go with an rotations, or with a swap. So that is left to the user on best, and which set of gates I get the best result. So here I have chosen YZ. So YZ combination is given by RX and polygate. So RX poly, this one complete block gives one of the circuit of poly YZ. So I have taken this 3 repetition. So I'll be having 3 different sets to do this classification. So once I draw this feature map, so this is the feature map now which I'm using for classification. So take this feature map, training, test, total set of data, and multi-class extension. So this is very important. So whenever you have the data with only 2 classes, make this as binary. So when there are more number of classes, since my data set has 3 classes, I have taken my class as all pairs. So choose this as all pairs and give this as SVM. Again, how to what is this multi-class extension? What is this all pairs? It has a very big explanation. So given a time, I can do that. So take all these features and feed it to an sum of the variable. I name that variable as SVM. So now our data is in SVM. So now again choose this quantum instance. Quantum instance is nothing but on this circuit is made to run on which processor. So this since it is a quantum circuit, I want to run it on a quantum processor itself. So for that, select the backend, and how many number of times the circuit has to run, because since it gives an output in a probabilistic nature, multiple number of times it has to be run to collapse into a proper output. So I'll choose the, by default the shorts is chosen to be 1024. And seeds, I have already mentioned the number of seeds as 10,000 here. The same thing I am putting here. Now my quantum instance is also ready. That is the computer or the processor on which I am running this. Now take this quantum instance and put my SVM is the variable where I had all this feature map, and make this quantum instance to run. This SVM algorithm is put into a quantum instance, and this SVM algorithm is processed on a quantum machine. And now I have the results obtained here. So this results can be seen. The testing accuracy which I have is 98.14. So if I see this classical, the accuracy, the third parameter was 96.15. So here I have the accuracy as 98.14. So this I have achieved because I have chosen a best poly feature map to give this accuracy. So at the one stand itself, I cannot decide which feature gives and this type of result. I have to make different trials to find out at what point I get this accuracy. So after this, you can also see the timing, how much time this process has taken to finish, and other things are similar. So only thing is we train it and see the result, and all other performance metrics are similar to that of a classical type. We can see the decision boundary, confusion matrix, uh, and ROC curve, and various other formats similar to that of a classical machine. So this is the process which we have in a quantum machine. So here in this SVM, I have just shown you a forward propagation. I have not introduced into a neural network concept. Now you got an output something around 98.15. Now for this output, since the output is collapsed to a classical type, now you can find out a loss function at this output which is similar to the classical type. With that loss, you can find out which optimizer to use to update this loss and give back the optimizer to the encoding, that is the feature map, to fine tune it and throw the output again. So it is like you can make this machine learning process as a neural network concept, and you can give a backward propagation and you can still improve the accuracy. So that is the next part which we can play around to improve the performance metrics of this machine learning with respect to the quantum. And this is one method which I have shown you is the QSVM classification type. So when we have this classification or the machine learning models, particularly with respect to the supervised learning, we have different methods, like we have the kernel methods, we have the variational quantum circuits method, we have neural network classifier methods. So you can IBM Quantum Labs has given beautiful tutorials on how to explore this machine learning or neural network concepts. So you can take any of the data sets and you can put your data set here and choose the feature map correctly and find out the performance metrics. So that is the part of the coding. So where we are now, what are the quantum computers we have today are the one uh, more publicly approachable quantum computers which we have is the IBM Quantum Qiskit. Along with that, we have the QCI, Xanadu, Alibaba, Honeywell, Google Serve, DWave System, Microsoft, Azure Quantum, Rigidity, and Amazon's. So these are the other companies also which are working on the quantum machines. And why those quantum machines are still not in a market, why it has not still has not become so popular is the one thing is it is very expensive, and And also when this architecture has to be built, it has to be, since we are working on an atomic level, a very little variation in the temperature make the complete change in the behavior of an atoms. So this atoms has to be maintained in a very low temperature, and all this has to do the computation at a very very low temperature. So this is because this is making a system itself as huge, and this makes also a cost very costly. And this entanglement, also I have told about the qubits, has a very beautiful principle of entanglement. And entanglement between the two atoms can extend only for a short period of time. So that is again one of the limitations which we have with the qubits. And since these qubits are very much error prone, any small change in a behavior of a qubits, with the temperature changes or with any extra environmental calamities, can change its complete behavior. So the coherence rate, or we call it as an error rates of the qubits, are very huge. So the main research challenge is also going to how to decrease this errors. We call it as a decoherence effects of these qubits has to be reduced. So till now we call this quantum computers as a NISQ computers, that is the noisy intermediate scale quantum computers. Still the complete quantum computers are not available. Only the NISQ type quantum computers are available. So with this limitations, and we are expecting the quantum computers, if we find out some measures to overcome all these limitations, and will be expecting this quantum computers to be in a market which can speed up the computation of the classical machine. Along with us, I want to point out some of the things. There are some false claims like the quantum computers will be completely replacing the classical machines. That is very wrong. It will not be replacing the classical machine. It is just a byproduct to the classical machine. That is, it will be enhancing the speed of the classical machine. That's all the quantum machines does. The quantum machine technique is just to increase the speed of the computation. So that by using a different type of or a different method of computation, it is increasing the computation speed. That is the only thing the quantum machines are doing. So that is one false claim we have. And also people says that quantum machines completely breaks the cryptography algorithm. So that is also false. The quantum cryptography, it only solves the cryptographic problem at a faster rate, but it does not breaks the complete RSA or any cryptographic type of algorithms. So complete hacking type of things is not done by the quantum machines. So this false claims has to be ignored. And so if all these limitations which we have with the quantum machines are overcome, so we can expect the quantum machines to be in market very soon. So that's all I have with this talk. And thank you all for providing me an opportunity to deliver this talk. Thank you,
Thank you,
Manjula
Manjula
ma'am, and
ma'am,
the
and the
entire
entire
team.
team.
All the best wishes. Thank you
Thank you,
all.
Manjula.